Hello. Today we're going to cover Chapter 8. Hello. Today we're going to cover Chapter 8, which is an introduction to hypothesis testing. Our learning objectives for this video is to understand the logic of hypothesis testing, and then we'll learn how to state the hypothesis and locate the critical region. So when we're talking about hypothesis testing, we're talking about a statistical method that uses sample data to evaluate the validity of a hypothesis about a population. So that's one of the reasons why in that last chapter, Chapter 7, we moved from talking about scores from a population and comparing a single score from a population, comparing a single score to a population mean, to looking at sample data and looking at those sample means and comparing those to the population. So here we have a known population before treatment, and it has a given mean that we know and a standard deviation that we know. The idea is that with hypothesis testing, that population undergoes some treatment and then it comes out the other side with a different population mean, or so we predict. And so we're going to talk about hypotheses that are related to that. The standard deviation stays the same because ideally that treatment will change everybody in approximately the same way. So your variance doesn't change, it's just that population. So here's really a little bit more specific about what we're looking at is typically you have a population and you have a known mean perhaps. You pick a sample, remember a representative sample from that population, it undergoes some treatment and you end up with a treated sample and a treated sample mean. What we want to do is assume that that treated sample mean will generalize to the population. And so we're comparing this kind of unknown treated population mean to the known treated population mean to see if there's a change. So we're going to go through a teacher-led example. So if you haven't yet, please download and print out the teacher-led and student-led practice problems. We'll go through, it'll be a couple of videos to take you through the whole thing, but please have that downloaded and printed out so you can access it when needed. So we're going to come across these 4 steps in hypothesis testing quite often. And the 4 steps are state the hypothesis, set the criteria for the decision, collect the data and compute the sample statistics, and then make a decision. So again, we're going to come back to these 4 steps pretty much throughout the remainder of the semester. So we're going to go through these very slowly right now. We'll cover the first 2 in this video, and then you'll come back and cover the next 2 in the next video. And we're going to do so going over an example. So the example says a training program designed to have an effect on friendliness is tried on 1 individual randomly selected from the general public. That 1 individual is our sample, and yes, it's an N of 1, but that's what we're going to use for this example to make it easier on us. And the general public is our population. Among the general public who do not get this training program, the mean on friendliness measure is 30. So we have a mean here of 30 with a standard deviation of 4. The researchers want to test their hypothesis at the 5% significance level, and we'll talk more about that later on. After going through the training program, this individual, so our N of 1, takes a friendliness measure and gets a score of 40. What should the researchers conclude? Can the researchers conclude that the training program had an effect on friendliness? So the first thing we need to do is state our hypothesis. And I guess the question is, what is a hypothesis? It's going to be our best prediction of what the treatment could do to that population. So we're going to have a null hypothesis, and the null hypothesis is noted as H sub O, and it states that the treatment has no effect. So we had that original sample mean of mu equals 30. So what we want to say is that there's no change or difference or relationship between that original population mean and the population mean after treatment. Another way of saying it is that the independent variable has no effect on the dependent variable. And so we're going to write it like this. We have mu sub O. We have mu sub O. And then we have our mean of our population, which was 30, equals the mean of the treated population. And so these subscripts are helpful to keep straight what means you're talking about. Now, the alternative hypothesis, written as H sub 1, states that there is a change or a difference in the general population. So after the population goes through the treatment, there is a difference in the population mean. So here is the notation, H sub 1, the mean of the treatment group, is going to be different than the mean of the population. So one of the things we said we knew is that our mean was 30, right? And this is our population mean. So our null hypothesis here is going to be that the mean after training is going to be the same as our population mean. So H sub O, the mean after the training, is the same as our population mean. A way of putting it in words is the training has no effect on friendliness. Now, our alternative hypothesis says that there is a difference. So we're going to say that the mean for training doesn't equal the population mean of 30. A way of putting it in words is the training has an effect on friendliness and will cause a change in the mean score. So it's important to be able to write both these types of null and alternative hypotheses, as well as understand the wording that would go along with them. So next we need to set the decision criterion. Now, when we do that, what we're going to see is the distribution of sample outcomes is divided. We have sample scores that are going to be close to the null hypothesis, and then we have those that are going to be very different from the null hypothesis. And so that's what you're seeing here. So you see these lines drawn here. We'll see that these lines are kind of arbitrary, but that's our decision criteria. That's going to be our significance level or our p-value. And as you see, as we draw these arbitrary lines, we have these tails out here, and we have two tails. So that's why it's going to be called a two-tailed test. And in these tails, it's an extremely low probability values if the null hypothesis was true. So if the mean was 30 in our treated population, these scores would be very, very unlikely on both sides of the distribution, in both tails, the two tails. Now we have these means here in the middle. And these sample means close to the null hypothesis, there's a very high probability. So if the null hypothesis is true, there's a high probability that these scores will fall in there. And it depends on what number we pick. This is called the alpha level. So these arbitrary lines are determined by our alpha level or our significance level. Now, on the last page, we said that our alpha level was, our significance level was 5%. If we turn that into a probability, probability is 0.05. So in both of these tails, there's a 5% chance that the scores will fall in these tails if the population mean doesn't change, or the probability is 0.05. So it's a probability value used to define these very unlikely outcomes in these tails. Again, they're boundaries. So see how this is a line? Think of it as a boundary. And out here is that critical region. This is the critical region. And so if your treated population mean falls, or sample mean falls in this critical region, we're going to reject that null hypothesis. And we're going to use those, the z-scores and that unit normal table again to determine what these boundaries are. Some common significant levels are 0.05, which is what we're talking about here, 5%. Another one is 0.01, which is 1% of the scores fall out in that critical region if the null hypothesis is true. And another very common one, and probably the one that scientists are pushing for more and more, is this 0.001 p-value. So here again, we'll get to the unit normal table in a minute, but just kind of re-emphasize what we said. Here we have that normal distribution of our population. Population mean is 16. For a z-score, it would be 0. And if we use 0.05 as our p-value, because we had a 5% significance level, which means alpha equals 0.05, the z-score is going to correspond to 1.96, and I'll show you why in the table, the next slide in just a minute. We're at the unit normal table, and we see I said that critical region was 1.96. I said that critical region was 1.96 here. Okay, now if we look over here, 0.025 is that proportion. So why would that be? Now remember, we have two tails. We have 1, 2 tails here. And those are the areas, and again, this is my critical Z, this is my critical Z. I have to take this 0.05 and I have to break it up into 2. So I'm going to take this 5% and I'm going to divide it into 2, which gives me 0.25%. If I take that and I change 2.5% into a probability, that gives me 0.025. And that's the number that I have here in my unit normal table. All right, so again, here we have 2.5% in this tail, the first tail, 2.5% in the second tail, and so that's a total of 5% in that extreme critical region, but 95%, if the null hypothesis is true, are likely to fall in between those critical boundaries.